4 p.m. Right, who is the first speaker? Jinbo Xu, right? No, please. I'll stop you 2 minutes. After 15 minutes, you have another 2 minutes.
Okay. Okay. Yeah. So I'll start. So thank you so much for coming to my talk. So in this talk, I'm going to talk about the deep learning method for distance prediction instead of contact prediction, and then apply this to protein threading, which is a very old problem. So we know template-based modeling is a very important method for protein structure prediction. And the popular method is based on sequence or sequence profile. So if the two proteins have similar sequences, then likely they will have similar structures. Okay. So a sequence-based method is not very sensitive, and then we have a profile-based method. So profile method we use the residue conservation information in a protein family. So instead of using a single sequence, the profile using information in a protein family. Then we can represent the protein family by like a profile such as the position-specific scoring matrix or hidden map model. Then we can compare the PSSM matrix or with the hidden map model to localize the correct fold. So this kind of profile method works for some remote homologs, but also miss a lot for homologs. So these are two very popular methods for template-based modeling. Today I'm going to talk about something different. So in addition to these two methods, there are also another method called threading. Many threading methods many years ago, threading method used the pairwise information to align the sequence to a structure. So different from these two popular methods. But the pairwise information is not very useful, not very sensitive enough. So at least before when we use applied pairwise information. So today I'm going to talk about how we can use the pairwise information to significantly improve the alignment accuracy. So the main idea of this talk is, so in addition to use the residue conservation information to do the protein alignment, we make use of the long-range inter-residue interaction information to significantly improve both the alignment accuracy and also the template selection accuracy. And so when we couldn't find close homologs in the PDB. So this is the main idea. So actually, the pairwise information has been tried many times before for protein threading, but we didn't observe significant benefit before. This is because before, most likely the pairwise information for the query sequence is not very accurate. But today I'm going to show you now we can have very accurate information, pairwise information for the query sequence. Then why the pairwise information now works? This is actually built on my previous work. So this is built on my work published in early in 2017. So early in 2017, I published one paper about which is the first one, introduce the deep convolution neural network to do the protein contact prediction. So by using the deep convolution neural network, we can significantly improve the protein contact prediction. And this paper just won the +CB research prize in the category of breakthrough. So in this paper, we published some key insights about the contact prediction. So first, we have to model the whole contact map as an image. So we predict all contacts of a protein simultaneously. By this way, then we can model contact occurrence patterns easily. So you can interpret the contact occurrence pattern as a structure motif. And so then we apply the deep convolution neural network to the whole contact map instead of just a pair of residues. So by using this way, then we can significantly improve the contact prediction. And so this is different from the deep belief networks, which are studied by Jennings Chen. So the deep belief network couldn't make use of these two key insights. So the deep belief network are not very useful. And so our deep convolution neural network differ from the pure convolution method in two aspects. First one is our deep learning will use the contact patterns in structures, but the convolution only care about the pairwise relationship. And we also learn the contact patterns from thousands of solved structures, while convolution only uses information in a single protein family. So this is why, by using the deep convolution neural, we can do much better than the pure convolution methods. And here is just I've just briefly introduced my deep convolution neural for the for contact prediction, and this morning Janice already did a very good introduction. So the input is a multiple sequence alignment. So from the multiple sequence alignment, we derive two features. One is the sequential feature, like for the sequential features, for example, is the residue conservation, and we also have the pairwise feature. So we can have the convolution, like mutual information, and we can also do the direct coupling analysis. Also have the pairwise statistical potential. Then we feed these two types of features information into our deep network. Then we will predict the whole contact matrix or the whole distance matrix. So here is our network architecture. Because we have two types of features, one is sequential features, the other is pairwise feature. So our network has two major components. The left one, the left column, is the component to deal with the sequential feature. So we do the 1D convolution transformation on the sequential feature. And the right column is the 2D convolution neural network. So this 2D is used to apply the convolution operation to the 2D features. Then the middle column is just used to convert the 1D feature into the 2D feature. So this is the basic idea of our network architecture. And then finally, we can output the whole contact matrix or the whole distance matrix. And here I just show you some results. If you are interested in more details, you can go to read our papers. In our paper, we have lots of results. Here, I just show you our post-Casimir-1 results. And especially, we care more about the long-range accuracy. So the first three methods are the pure convolution method. And this one is the shared neural network method. And this is our method, the result of our method. So you can see here, compared to the pure convolution method, our accuracy is significantly better, so much better, more than doubled the accuracy when you look at the top L over 2 accuracy. So this is CASP-11, and we partially implemented our algorithm for CASP-12. We didn't finish implement this algorithm before CASP-12 terminated, but still our method got the best F1 score, much better than all the other methods by using our deep neural network method. And so in our paper, we have more detailed CASP-12 results. And actually, our new results on CASP-12 was published in August 2017. It's not in 2018. And our accuracy, knowledge accuracy is 59%. It's not 56.8%. I don't know where he got my results. So this is our updated results on CASP-12. And so I also, before this talk, I also did some simple literature survey. And so there are many now new work on applied deep learning to contact prediction. So our work was further validated by quite a few papers. They just do some modification of our network architecture to the contact prediction. And although there are many new publications, but I only noticed two papers which may show some further improvement. So one is from the Yaoqi Zhou's group, and he did a very comprehensive benchmark for all the recent methods. And the other group is Haipeng Guang from the Tsinghua University. So he used a very interesting method to further improve our prediction results. So this is a new development. So in this talk, instead of do the contact prediction, I do distance prediction because I wanted to do threading. Actually, contact information is not detailed enough. So here I just show you the distance prediction error. So in these two pictures, the x is the log of the MSA depth. And the y, in the left picture, the y is the absolute error, and the right picture shows you the relative error. So you can see when the MSA has more information, has more sequence, then we can significantly improve the prediction accuracy. And the results here are just are pretty old, and then right now we have much better results than what I show you here. So this is the distance prediction error. So once we have the predicted distance, then we can apply the predicted distance to do the threading to align the query sequence to a template. So then how we can do the alignment? So here I show you how we can do the alignment. Suppose we have a template here, and we have a query sequence here. Then we use one variable z to indicate we can align this position to this position. And then we use this variable to indicate this position and then to this position. And we also have two parameters, theta. Theta is just like the energy function, the potential. So this one is to measure how well to align this position to this position. And this theta is used to measure how well to align this pair of residue to this pair of residue. So we have this kind of scoring function to measure the quality of one alignment. And so for this theta, so we just use a typical scoring function. And for this one, we use this scoring function to measure how well to align two pairs of residues. So here, DIKT is the distance in the template, and this is the distance in the sequence. And this is just the background probability of this distance. So you can get this background probability by statistics. And this one is predicted from our deep neural network. So this is our scoring function to measure how well to align two pairs of residues. So once we have this scoring function, then we need to optimize. So then how we can optimize this problem? So this problem is NP hard, so it's computationally hard. Once you consider the pairwise interaction, then this problem is NP hard. And then how we can do this? How we can optimize this scaling function? And back to 2014, we developed an algorithm which can align two protein families when you consider the pairwise relationship. So this paper was published in 2014. And so we model a protein family using macro-random fields. Then we align two macro-random fields to do the homology detection. So this is the major idea of this paper. So we just apply this algorithm in this paper to this to align a sequence to a template. Then we can get the alignment. And so because I don't have much time, I'll just skip this algorithm. And so I'm going to show you some results. So I compare just our new strategy method with HH-PRIT, which is a hidden map model-based method, which is very sensitive. And also compared to CF-PRIT, which is our in-house strategy method. So CF-PRIT use information more than sequence profile, but it doesn't use the pairwise information. And eigenthread is a new thread method, but eigenthread only uses the context, didn't use distance information. And we measure the quality of alignment or a model by TM score and the GDT score. Here, in this talk, I'm going to show you the TM score. So first, I randomly sampled 1,000 protein pairs, and then use all this threading method, to align them to see how well we can align them, and then compare with HH-PRIT. So this picture compare with HH-PRIT, and this compare with our CF-PRIT. So the major difference between our deep threading method with the CF-PRIT is in our deep threading method we use pairwise information, but in the CF-PRIT we don't use pairwise information. So from this comparison, you can see, so for most of the protein pairs, we can do significantly better alignment than the hidden map model-based method. And this picture shows us, so when we use the pairwise information, use the predicted distance, we can significantly improve the alignment. So this is the accuracy on the alignment, this is the performance on the alignment accuracy. Then here I show you the threading performance. So I thread the test proteins into a database, like say BC40. So the left picture shows you the threading performance on 5,000 test proteins and compare with our CF-PRIT. And the right picture shows you the threading performance on the 86 Cas12 domains. So from here you can see again, right? So the deep threading method works much better than the when you don't use the pairwise distance information. So on both very different test sets, so we observe the same trend. And so then we wanted to know in which case the pairwise distance is useful, can improve the accuracy. So here we did a study. We studied the improvement, the relationship between the improvement and the multiple sequence alignment information in the multiple sequence alignment. So we measured the information amount in a multiple sequence alignment by the multiple sequence alignment depth. And we just look at the cuffed hard targets. So in total, there are about 50 cuffed hard targets. Then we draw a picture show you. So the X in this picture is the log of the MSL depth, and the Y is the improvement. So from here you can see for most of the targets, so we can improve the modeling accuracy, but also for some, so the deep thread works worse. And especially when you don't have too much information, so in this region, so sometimes it's hard to say if you can improve or not. So generally speaking, when you have more than 10 sequences in the multiple sequence alignment, then there's a good chance you can improve the alignment by using the distance information. But when you only have 1 or 2 sequences in the multiple sequence alignment, maybe it's dangerous to use the pairwise information. And here I just use this table to summarize the CASP12, our results on CASP12 targets. So the CASP split all the CASP domains into 3 categories. So the first one is the free modeling, which is the hardest targets. And then it's the template-based modeling, which is the easy targets. And this category is just have a medium difficulty. So we look at the performance on these 3 different CASP targets, and we also compare with HH plate against red, CM plate, and our this deep red method. Yeah, so you can see here. So the largest improvement is in this category. Yeah. So for the easy targets, we can slightly improve over our CF plate, but the improvement is not very big. And for this one, we can improve, but it's not big either, just because for the fluid modeling in the database, we simply don't have templates. So the largest improvement is in this category, because in this category, we have templates in the database, but we just couldn't recognize it, or we couldn't build a good alignment. So by using the pairwise distance information, then we can build a much better alignment, so we can recognize the correct templates. So this is why, in this category, we can significantly improve the modeling accuracy. Okay, so here I will just summarize. So now by using deep learning with the convolution, we can predict much more accurate inter-residue distance than before. And this kind of distance information is useful for protein alignment and protein modeling. And so the predicted distance is mainly useful for the targets without so close templates in the PDB. And for those targets without templates in the PDB, actually, we don't have to use threading. We can use Abel-Ishida folding, which can do much better than the threading method. OK, thank you so much. I'll stop here.
OK, we have time for a few questions.
This is just a clarification question. So when you showed the alignment with the theta and the z, was it coevolution information for both families or for just one?
Just for one. For template, we use the relative distance information.
Have you thought about aligning where you have the coevolution information for the structure and for the query?
Yeah, I think we can definitely try, but I just didn't get the time to do that. Yeah, but I think it's worth to do that. Yeah.
Thanks for your talk. This is also a clarification question. So you showed that you extracted your features from multiple sequence alignment.
Right.
So after you train your model, and if you're seeing a completely new protein, how would you extract those features? Would you go back and align with all of the input proteins all over again?
No, for the multiple sequence alignment, it's produced by another tool, not by our tool. Yeah, so like you can use a homology search tool like HH Blitz, or you can use BLAST to produce the multiple sequence alignment.
I see. So you would use those tools and generate a whole new set of features.
Yeah, we use them to produce the multiple sequence alignment, then we will generate feature by ourselves from the multiple sequence alignment.
Okay, thank you.
Any more questions? So let me just ask another clarification question. When you say easy target, difficult target, you use the same method everywhere. You don't change the...
Exactly. So here all are fully automated benchmarks, so we don't do any manual intervention.